Hello everyone, good evening. Welcome to Nrcm. This is Shravani and I'm going to explain the operating system subject of Unit 3, and the topics I'm going to explain today are Peterson Solution and problems of synchronization. So now let's go to the video. So first is Peterson Solutions. The Peterson Solution is a classical software, and it is based on the solution to the critical section problem. Means it provides a solution to the critical section problems. So here I think you can see, so this flag is there. So this is the flag. So this flag will be initially it will be false. So if if this is false, okay, I'm speaking about the true. If the flag is true, then we can say that some of the process has entered into the critical section. If the flag is false, no other process has entered into the critical section. And next in turn, like turn is equal to, what is the meaning of this turn? Like turn is the process whose turn is to enter into the critical section. Like next after the process and one process enters into the critical section, and next it will be giving the turn. So whose turn next, the next process has to be entered into the critical section. In simple, the process whose turn, it defines the whose turn it is to enter into the critical section. Okay, and this and I think this is like once after this is declared, then while if these conditions are true, then it will be entering into the critical section. So once if it is everything is execution, then again it will come back. Okay, so your Peterson solution it preserves all three conditions. What are the three conditions we have discussed in the previous slides? Like first one is mutual, like it should preserve the mutual exclusion. So it assures as only one process can access the critical section at any time, so that it should satisfy. And next it assures like progress is also assured as a process outside the critical section does not block another process from entering the critical section. And next, bounded waiting is preserved as every process gets a fair chance. So these are, the Peterson solution, it will preserves, or it will check all these conditions, all three conditions are satisfied or no. And there is a disadvantage in this Peterson solution as well. So the first disadvantage I can say is like it involves much busy waiting, because if there is already flag here, so here the turn process will be in waiting stage. And the second limitation is it is limited only to the two processes, one process which is executing and one process which is in waiting stage. So that will be the, according to me, that are the two disadvantages. And next we are going for the classical problems of synchronization. See, so what are the problems of some synchronization? The following are they, the two, like bounded buffer problem and the problem statement. These both are like classical problems of synchronization. So as we all know, like bounded buffer problem is like a producer consumer problem, which this bounded buffer problem is also called as producer consumer problem. So it is one of the classic problem of synchronization. And next, coming to the problem statement. Suppose, as you can see in the diagram, like if there is a buffer, so this is a buffer, this is a total buffer, which is having n slots. So these are n slots, and each slot will be capable of storing 1 unit of data. And here there are two different processes, that is producer and consumer, which are running or which are operating. So producer is filling from this way and consumer is filling in this way. So first this will be the problem statement. So first, before this, I just wanted to explain what is bounded buffer problem. So first of all, coming to this bounded buffer problem, so it shows like suppose the producer tries to insert the data into an empty slot. The processor tries to insert any of the empty data into the buffer. So then consumer, what he will try to remove the data from the filled slot in the different buffer. As you might have guessed by now, those two processes won't produce the expected output, right? This is true if they are being executed concurrently. Even though if they're executing concurrently, they cannot produce the expected output. So there needs to be, there needs to be a way to make the producer and consumer work in an independent manner. Okay, now let's find the solution for this. So one of the solution is like, so this is the solution slide, and one of the solution of this problem is to use the semaphores. So we have to use the semaphores for this kind of bounded buffer problem. The semaphores are like, so here it is declared like M is, it is a binary semaphore which is used to acquire and release the lock. So here the acquire and release the lock, like M can be either 0 or 1. So you can set the values as 0 or 1 or true or false also. If 1 indicates there is some process entered into the section, critical section, and 0 is like there is no other process present in the section. So next is empty. Empty means here it's counting a semaphore whose initial value is the number of the slots in the buffer. So since initially all the slots are empty, so empty is like, so it will count how many unit of how many slots are filled. If no slots are filled, then it will indicate the, so empty is like if no slots are filled, it will indicate the empty. Next, full is like counting a semaphore whose initial value is 0. And next, at any instant, the current value of the empty represents the number of empty slots. So empty represents the number of empty slots, and full represents how many slots have been occupied in the buffer. So next, I just wanted to show this like Sudoku. This is one is for producer, this is for producer, and next Sudoku is for the consumer operation. So by looking at this Sudoku, looking the like above code for producer, we can see that the producer first waits until there is at least one empty slot, right? So first wait empty is there, so he'll be waiting, the producer will be waiting until there is at least one empty slot. So then what he will do, he decrements the empty semaphore because there will now be one less empty slot, since the producer is going to insert the data in one of these slots. Then it acquires lock on the buffer so that the consumer cannot access the buffer until the producer completes its operation. After performing the insert operation, the lock is released and the value of full is incremented because the producer has just filled a slot in the buffer. I hope by checking this Sudoku, you have understood what is this producer operation, how the producer operation will happen. Now we are going to see about this consumer operation. So in the consumer, like here what happens, so first of all it is here wait, right? So the consumer waits until there is at least one full slot in the buffer, and then it decrements the full semaphore because the number of occupied slots will be decreased by 1. So after the consumer completes its operation, so once until the after the consumer completes its operation, then the consumer acquires the lock on the buffer. So then following that, the consumer completes the removal operation so that the data from one of the full slot is removed. Then the consumer releases the lock. Finally, the empty semaphore is incremented by 1 because the consumer has just removed the data from an occupied slot. So it is making it as an empty. So this is about the consumer operation. So on the next slide, we are going with the writers problem. So here, like in this problem, what happens in reader writers problem, there are some processes. The processes are called as readers, as we have mentioned here. There are some processes which are called as readers. What they'll do, they'll only read the shared data, and then they will never change it. And there are other processes which are called as writers, who may change the data in any addition to reading or instead of reading it. So there are various types of reader writers problems, like most centered on relative priorities of readers and writers are. So first one is dining philosopher problem. So first is this dining philosopher problem. So here the dining philosopher problem, it is a classic synchronization problem. As we all know, that is classic synchronization problem. So which is used to evaluate situations where there is a need of allocating multiple resources to multiple processes. So this occurs if there are multiple resources which has to be allocated to the multiple processes. So here comes here. So here what happens, like the dining philosopher from. And coming to this here, the statement we can give like that: the dining philosopher problems involves the allocation of limited resources from a group of processes in a deadlock free and starvation free manner. See, by considering this, see if this is the dining philosopher problem. So this is the dining table you can consider. So there are 5 philosophers. So here this is philosopher 1, 2, 3, 4, 5. There are 5 philosophers who are sitting around the table, in which there are 5 chopsticks. I think you can see these are the 5 different chopsticks kept beside them, and the bowl of the rice in the center. So as you can see, like this is the bowl of the rice in the center. When a philosopher wants to eat, he uses 2 chopsticks, one from their left and one from their right. Okay, but when the philosopher wants to think, he keeps down the both chopsticks at their original place. So, so this is the problem. So there are only 5 chopsticks, and each philosopher uses the 2 different chopsticks. So how to solve this? Like, is so from the problem statements, it is clear that the philosopher can think for an indefinite amount of time, but when the philosopher starts eating, he has to stop at some point of time. The philosopher is in an endless cycle of thinking and eating. So the sudoku or the solution for this is like, so there are chopsticks. You can see, like there are 5 chopsticks. So for each of these 5 chopsticks, so this I mean for each of the philosophers there are 5 chopsticks. So here when the philosopher wants to eat the rice, he will wait for the chopstick at his left hand, picks up the chopsticks, then he waits for the right chopsticks to be available, and then picks it too. After eating, he puts both the chopsticks down. But if all 5 philosophers are hungry simultaneously and each of them pick up one chopstick, then a deadlock situation occurs because they will be waiting for another chopstick forever. The possible solutions for this might be like, the philosopher must be allowed to pick up the chopsticks only if both the left and right chopsticks are available. If only if suppose if P1 is there, so if his left and right chopsticks are available, then only we should allow him to pick up. So and allow only 4 philosophers. See, there are 5 philosophers, but here we should allow only four philosophers to sit to sit to sit at the table. So, and if all the 4 philosophers pick up 4 chopsticks, there will be one chopstick left on the table. So one philosopher can start eating, and eventually 2 chopsticks will be available. So in this way, the deadlocks can be avoided. So this is the solution for the this are this is a solution for our dining philosopher problem. And thank you.